Hello everyone. So I'm going to continue working on the dataset, wine dataset, and last time I forgot to actually show you a kind of new way to read a dataset. So this was one of the way I always show you to read the CSV file, and the other way is actually to do this data set pd dot read underline table and the path. Okay, let me show you what happens. First, I'm going to print the data set dot head 3, and then I'm going to print the data set dot shape. Okay, so if I create this data set using read table, actually reading CSV file using read table, what happens? Do you see what's going on? So all the numbers in the data set are connected or separated by comma, right? Because this is a comma separated file, correct? So when I read a CSV using read CSV, the file are going to be shown this way, like a table. When I read the CSV file with table, I must mention that separate the files with comma. Then in this way, I'm going to have a data like this. But let's remove print. Then now you will see this similar form as the data set you saw when I read the data set with CSV file. So there are two different ways, but just remember, if you're reading the table using read table, reading the CSV, you must mention that the separation delimiter is comma. Okay, so what we were doing last time, let me show you. Let me save this and let's go back. So what we had last time we showed this box plot. We were talking about outlier, and I showed you the simplest way to detect the outlier. And what I did exactly, I went through just one variable, for example alcohol, detecting outlier in just one variable, and the variable I was talking about is alcohol, and the method I used was interquartile range, right? But there are different methods to detect outlier. So when the data set is the low dimensional data set means you don't have that many rows, you don't have that many columns, because sometimes the data set can have like 1 million, 2 million rows, and there are some data set actually are 5-6 gig, and it's so difficult that you download those kind of data set on your computer, and you must use HPC, high performance computing method, to be able to read those kind of data set and have a look at those data sets. So there are some data set that has a really high dimension, and then in those kind of situation, let's say we have gene expression data set. What is that? They are going to show the transcript DNA for each gene. We have 23,000 genes, for example, for human. I mean, almost that much. And for all these gene, they are going to, for example, have samples in the data set. So what that means one of the samples, they extract DNA transcript for all 23,000 genes, and then another sample, they will extract the gene information for all the genes, right? And then they don't have one or two samples. Sometimes they have almost 200, 300 different samples, right, in their experiment. So imagine what can be that data set, the data set with 200 columns in parentheses samples, and will have like 23,000 or more than that genes in each row. And all the actually inputs, all the values for DNA transcript will have different scales, because each gene will kind of show different size of transcript DNA. And what else, some of the genes will not even show, some of the samples will not even show DNA transcript, means there's a 0 value, and other samples have a really high value. So all of these things are creating a high dimensional data set, which is sometimes very complex, very difficult to work with. So in those kind of situation, you are not going to bring out just one variable alcohol and find a outlier for that, right? You are going to, for example, find some of the genes as outliers, means they don't have DNA transcript for some samples or for most of samples, or you will find some of the samples that are misleading and have a wrong information of DNA transcript. So either you are going to remove samples that are outliers, or you are going to remove some of the genes that don't have information. So these are all the situations you are going to go through. So this is the simplest form of outlier, observing outlier in the data set. But generally, for those who even don't know what is outliers are the observations that are falling outside of the overall patterns. If I go to the this one, for example, this what is that, histogram, you will see the frequency. What is the frequency? Frequency is the height of each of these bins, right? Class intervals. So it shows almost 650, for example, wine have the residual sugar between this value on x-axis, right? Around these values on the x-axis. And then as the height of bean decreases, we'll have lower number of wine that have residual sugar around this boundary on the x-axis. And then what this means a few of wines, 2 or 3 or maybe one of wines, have the residual sugar very high. So if you draw a density curve on this histogram, you will see that this observation here, or observations maybe, fall outside of the overall pattern, and they are far from the rest of observations. So this observation here can be an outlier, and then we should inspect this observation further. We should look through our data set and see what's going on and why this observation is far from other data set, and what is the value, and what's the effect of this observation on the other variables. So here, for example, for volatile acidity also, we have some observations that count as maybe outlier, because they are outside of the overall pattern. And most of the time, actually, outliers like these cause a skewness, because the density curve will extend to the, for example, right side to cover this observation here, And that's the reason when we have skewness, we may suspect the presence of outliers in our data set. So skewness can be to the right side, can be to the left side, and then if it is to the right side, you will say, okay, outlier is on the right side, and if the skewness is on the left side, you will have a lower outlier because the outlier will be on this side. Okay, so let's look at this. So for example, for alcohol, we had just outlier on the right side or in higher value of alcohol, right? We didn't have any outlier on the lower value. And then here we have outliers on both sides. Here we have outliers that are exactly same. Why? Because the quality were more similar to a categorical variable. That's why we see this kind of pattern. Yeah, sometimes we can have lower outliers, sometimes we can have upper outliers, sometimes, most of the times, typically we will see a pattern like this one, and this one means outlier on the right side, and we have a right skewed distribution. Okay, so more about outlier. Outliers, actually, as I said, they are observations that lie outside of the overall pattern, right? And then outlier, what they can do, they can cause or result in poor fit and will affect on regression line, will affect on correlation. For example, if there is a really good correlation between two variables, height and weight or height and age, some outlier cause a bad effect on the correlation, means can decrease the correlation drastically, and that's the reason we say outlier can cause effect on the correlation. Outlier can cause effect on regression line because when we have an outlier can pull the regression line to itself. Because least square regression line tries to have the lowest square residual or lowest distance between each point to itself. So if we have an outlier which is very far from the least square regression line, the least square regression line is trying its best to get closer to the all the point on average, right? And then the high distance between outlier and least square regression line will cause a kind of bias in least square regression line. And then in classification also, the outlier can cause the difficulty in explaining the classification. And as I mentioned before, outlier can cause a skewness in the data set. So removal of outliers involves in eliminating the data point from the sample. And then we can also replace the outlier. Then replacement involves swapping the data point for the mean or median. So removal means you detect the outlier, remove the outlier from the data set. And then replacement means you are going to replace the outlier with mean or with median. So one, removal. These are two general kind of solution. One, removal. Another will be replacement. Okay, so there are different techniques to do that. And let me write down by median or mean of the data. And then removal means eliminating the outlier or outliers from the data set. Which one is better? You definitely should look at your data set and the purpose of your study, and then investigate this further and see which one benefits your type of data set more. You should not just make a decision without studying this further. Okay, so One of the simplest way, as I mentioned, to detect an influential point is to use interquartile range, and that happens whenever you have univariate, have kind of simple one variable data set. One variable, like here I just chose alcohol, and then I try to detect outlier here. And then the other kind of approach is the to build a model using regression model, for example, or other different model. I will show you. I will go through the removal of outlier using the model, building model. And then we call that multivariate method. If we build a model and then based on the model remove the outlier, or kind of manipulate outlier, we call that multivariate method. So the simplest approach was just working on one or two variables, remove the outlier, or kind of replace that with median or mean, and that method is univariate method. And then the other approach is building a model, and we call that approach multivariate method. So either removing or replacing, there will be some approach to detect outliers. One is simplest approach, and we call that univariate. And then other one is building model, and we call that multivariate approach. And there is another one which which will not remove the outlier, or which will not remove or replace outlier. And I don't have a good memory to memorize the name for approaches. Minquasi. Okay. So this approach will not remove or replace outlier. Instead, it will reduce the impact of outlier. Instead, will reduce the impact of outliers. So this approach is more logical, more reasonable, and it's based on the kind of it's not based on a standard sum square error. It's more to give a weight to the observations, and standardize the weight in order to create the better kind of equality in the data set, and kind of decrease the weight of, for example, outliers to be more similar to the other data set, and then it's going to just build a model based on this kind of adjustment, right? It's not going to remove or replace outliers. So these are the three main approaches to detect outlier and fix outlier. And we kind of talk about this one, and we never remove the outlier from the data set. But as I mentioned, when you are dealing with a complex data set, probably the best approach is to remove the outlier, because at some point, as I mentioned, for example, the gene expression data set, when some of the genes don't have any values in different samples, so what you want to do with that? Why do you want to keep those kind of genes when they don't explain enough about the data set? So the better way to deal with those kind of outliers are to just remove them from the data set. But when you're dealing with some of the data set, like economic data set, probably you should look into it and see what is the best approach to deal with outlier, either replacing them with mean or replacing them with median, because choice between mean and median is very critical. If our data is very skewed, median will not be affected with outlier, but mean will easily get affected by the outlier, and this is very critical. And even actually the basic thing I explained in my statistic classes when I'm talking about mean and median is about resistancy of mean and median. So mean is not a resistant measure to the outlier, but median is a resistant measure to the outlier. Why? Because median is in the middle of data set. Removing or adding a kind of huge observation will not affect the midpoint, but adding or removing huge data set will affect data observation, will affect mean. Why? Because mean is the summation of all the point, right? Adding a huge data or removing a huge data will affect on the summation. So now I didn't want to talk about this. I mean, I forgot even, but that's a good thing I talked about this, because now let's talk about the participation point. Participation point. So for your participation point, I want you to study this further. What is the resistant measure to the outlier? What are the resistant measure to the outlier? And you should explain each of them: mean, median, quartiles, and standard deviation. Okay, so I'm giving you 4 different measures: mean, median, quartiles, standard deviation. Which one of them is a resistant measure to the outlier? Which one is not? Why and why not? So if you are saying, for example, mean is not resistant to the outlier, why it's not? If you are saying median is, why? Quartile, yes or no, why? Standard deviation, yes or no, why? This is very important, and I hope you not just answer this question. I hope you study this further, because there's another actually participation point I wanted to talk about this in future, but now I think is the best time. Study about the outliers more and write down a paragraph of what you learned about the outliers, not what I explained. I want you to study this more and explain to me something that I haven't explained. So I want you to really study this topic more, because this was something for years when I was a student myself was bothering me. There, first of all, back then there was not as much as information that now you can find on the internet or from different books. There were not that many, tools to kind of browse the internet and find multiple websites and get lots of information. It was not like that, like this at all. So now you have the advantage, and it's very nice to go through this whatever article you find and learn more and increase your knowledge, and also bring something to me so I can learn from you. So you have two participation points. One is this one, another is this one for this lecture. So now, one of the approaches that people follow in machine learning actually is to split their data set to two parts. One part is the training data set, and another part is testing data set. So normally they get a percent of their original data set as a testing data set to validate their model, and the rest of their data set, let's say 75% of their data set, will be the training data set. So they build their data set on the training data set, and they use the test data set to test their model and see how accurate their model is for validation purposes. So in machine learning, to validate a statistical model, for example, they use part of data set as a training data set, a percentage of that, let's say 75%, and the other smaller part of their data set, they are going to use that as test data set. So why they do that? To validate their training data set, their model that created based on the training data set. So for example, we would like to estimate the test error associated with, let's say, fitting a particular statistical learning method on a set of observation. So what they do, they separate their data set to two parts. They test their model that they are creating in part of data set, and they kind of validate their model, the built model, using the kind of testing data set to see how well their statistical method is kind of fitted. Okay, so as I mentioned, this is mostly in machine learning model. They need to set aside part of the data to be able to test how the model performs on the data that it hasn't seen before, for example. And in easier kind of word, training data set is the part of the data that built up a model, while a test or validation set is to validate the model that they built. Okay, so to detect the outlier and remove the outlier, also people, when they do machine learning, when they are working on machine learning data set, they use this kind of testing and training part of their data set to remove the outlier, detect the outlier, remove the outlier, and then they will compare the new kind of data set with the previous data set. So how they do that? They will, first of all, using testing and training data set to see how the detected and removed outliers will improve the data set. Okay, so what we are going to do, we are going to use a package sklearn that we already saw, and then model selection method. In this package we are going to import train underline test underline split. So we are going to create our data set from, we are going to create a data set from our data set using just the values in our data set. So let's see what I'm talking about. So these are only the numbers of the data set you see here. There's no column name, there's no row name. We are just using the values, and the values are stored in an array, right? So retrieving the values in our data set as the array. Okay, so what we do now, we are going to say we have an independent variable, and that independent variable is the last column of my data set. Why I am saying that? Because do you remember I said I want to keep the quality as my independent variable? Oh, sorry, dependent variable is the dependent variable which is in the last column of the data set. Correct? So the last column of data set, in parentheses, -1 shows the last column. And then now I'm going to define independent variables. So now what are those? Those are all the values, all the variables, except the last one, because the last one is going to be the dependent variable, right? All the columns except the last column, because the last column is the dependent variable. Quality. Okay, so what I created dependent variable from the data that are just the values, and I created independent variable which are just the columns that are all the columns which doesn't contain the dependent variable. Okay, so what I'm going to do next, I'm going to print some of the kind of aspect of this dependent and independent variable. So I'm going to say original data sets information. Oops, what happened? dataset information. So I'm going to see what is the shape of this dependent variable. I'm going to see what is the shape of this independent variable. So as we see, there are 1,599 rows and just one column for the dependent variable, and 1,599 rows and 11 column for dependent variables. So we have 11 independent variables, right? And just one dependent variable. So this is just a brief kind of explanation about our independent and dependent variable. So what I'm going to do next, I'm going to create independent training data set. I'm going to actually, these are all together. I'm going to create dependent train data set. I'm going to create two more variables. One is independent test data set, another is dependent test data set. So I have four variables. And where these four variables comes from this method, train underline test underline split, this one. So this method helps me to split the data set to four parts, not four variables, 4 parts, right? And what are the attributes or arguments in this train test split? First of all, I'm going to use the independent variable, original one I had. The second argument is going to be the dependent variable, right? And then the next data argument is going to be test size. If you don't choose the test size, by default the test size is 25. If you don't even choose this, that's okay. So, but you can choose the test size and say my test size will be like 33% or 30%. So 30% is written as decimal here, right? So let me write down here, by default test size is 0.25 or in parentheses 25%, right? So if test size is 25%, what is the train size? Train size is 75% of your data set, right? And then now that I chose 30, now the train size will be the 70%, right? It's not going to be 75% anymore. Okay, so we can choose train size, test size, all of this, right? Okay, I'm going to bring this down, bring this down, bring this down. So test size, what's the last one? Last one is random state equal 1. Okay, so there is more into this random state. So the random state, so the random state, it's a kind of mode that performs a random split, and the default is np.random. And what else? Basically, by setting this random state, you guarantee that the parameter in this package, a scale-learn package, provides a seed value to the function's internal, summarize the kind of shape of the train and test sets. So it's going to, this seeds value will going to explain the shape of train and test sets. And actually this definitely depends on the kind of model that you are feeding, and based on the model that we are going to explain later, the random states is going to adjust itself and change. Okay, so now let's see if everything is correct. Let's run this. So now we have independent training set, we have dependent training set, independent testing set, dependent testing set, right? So what I'm going to do here, I'm going to let me write it down. I'm going to print the information of training sets. Well, this one, I don't like the grammar. Information of the original data set. Much better. And then I want to print the information of testing data set. So I'm going to print this out for you to get more clue about what we have in this. So independent train and then dependent train. Okay, so I'm going to print this out. Let's see what we have. Okay, so independent train is going to be a kind of array like this. All the values that is part of your original data set. And then the next one is going to be all the values which are the part of your data set. This is just one column. This is going to be 11 columns, right? 1, 2, 3, and up to 11. This one is just one column. And then information for independent test. So this is going to be 11 and this is going to show 1, and then the rest is not showing. So what I'm going to do, I'm going to just print out the shape of each of these sets. So that's more convenient for us to look at. Okay, so now the shape. So the first says the original data has 1599 rows, means this much observations, right? And then dependent variable will have, let me switch this. Now, okay, so the independent variable will have 11 columns because we have 11 independent variable in our original data set, and then the dependent variable is just one column. And then now the training set will have 1119 rows. There is something wrong here because the rows for training data set should not be similar to the testing data set. Okay, so I should look into see where did I do something wrong, because I did something wrong somewhere. Okay, I will look into it and I should fix this. Okay, here it is. So now look at this one. So when I was explaining, actually I didn't pay attention. The two independents come first, and then we have the dependents. So it should be like independent train, independent test, and then dependent train, dependent test. This is what I was wrong. Let's run this. So now you will see. So now you will see the training data set has 1119 row, and the testing data set will have 480 rows. So this is the 30% of the data. This is the 70% of data. Let's change this to 25. You will see that we have 400 out of 1599 rows to be our testing data set, and then 1199 are the what is that, the training data set. Okay, so this is the way we separate the testing data set and training data set. The next step for us is going to be to fit the model, either using linear regression or using different kind of method, and then we evaluate model performance using the training data set on the test data set. And then what we do, we make a prediction on the test data set, and then we'll calculate the predictions using the mean absolute error, MAE. So MAE is something that I'm going to explain in next video, and then in next video I'm going to fit the model using 4 different models, and then we are going to compare the MAE. So we are going to create MAE, mean absolute error, for the original data set we have, and then we are going to fit the model and create MAE after removing outliers to see how the MAE is going to improve by removing the outliers. And then we will compare the data sets and their MAE to see how the data set improved after removing the outliers, if there are outliers in the data set. Okay, so we'll see you in the next video.